Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
All right, question 45 asks to review conceptual example 5 as background for this problem. That can be found on page 989. I recommend going through that before going through this problem, just to give yourself, a better idea of what's happening. Assuming you have. Question 45 states that an energetic proton is fired at a stationary proton. For the reaction to produce new particles, the two protons must approach each other within a distance of 8 × 10⁻15 meters. The moving proton must have a sufficient speed to overcome the repulsive Coulomb force. What must the minimum initial kinetic energy in MeV of the proton be? Okay, so it mentions, so we have two protons, the scenario here, using the notation of a previous problem. We have a moving proton basically interacting with a stationary proton. I shouldn't say that. It's not the arrow. I should have it as a plus, because that's our initial part of reaction to produce some reactants. So in order for this to occur, the protons must reach this distance shown here, given by R. And we have to find the moving proton must have a sufficient speed to overcome the repulsive Coulomb force. So maybe the first place to start is to find out what that Coulomb force is. Remember our equation for that, it'd be K, our Coulomb force constant, K times Q squared, or Q1 times Q2, I should say, divided by R squared. The force for each of these, well, we know the charge, so we can figure that out. 8.99 times 10 to the 9 is our Coulomb force term, with units of newtons meter squared over Coulomb squared, multiplied by, well, they're protons, so they both have charge positive E, so times E squared. E we know to be 1.6 times 10⁻19 coulombs, and divided by this distance of 8.0 times 10 to the 15 meters squared. And just to remember, our units are coulombs. Double check, this meter squared cancels this meter squared, Coulomb squared, Coulomb squared. Well, I guess it's coulombs, so that term in itself is squared. We are left with newtons. I mean, this repulsive Coulomb force as a state is 3.6 newtons. So if you think of the scenario now, we have a proton moving, and it remains stationary at some point near our stationary proton. So this kinetic energy that it's traveling with is converted into potential energy as the moving proton is stationary next to the stationary proton, right? So that means that our kinetic energy of this proton has to equal the potential energy of the two proton system. So to solve for potential energy, which I think typically it's given by U, we know that that is simply the Coulomb force multiplied by distance. So we take kinetic energy simply is our Coulomb force times R, that separation, and we should multiply this 3.6 newtons times our distance 8.0 times 10 to the negative 15. 10 to the negative 15, oh sorry, yeah, that's a very large distance otherwise. 15 meters, that was the same value if it was positive 50. I mean, the answer I provided here assumed that was negative, so my mistake for that one. Yeah, and with that calculation, we find that the kinetic energy required would be 2.88 times 10 to the negative 14 joules. Which, unfortunately, if you want to think of it that way, it asks for the answer in terms of MeV. So we know there are 1.6 times 10 to the negative 13 joules per 1 MeV. Our joules cancels out, and we're left with a mega electron volt value of 0.0 0.18 MeV. And there you go. So in this question, we recognize that this Coulomb force is the force between these two particles acting. The kinetic energy of this moving proton, given here, is converted to potential energy as it reaches that stationary proton. So this relationship held true, kinetic energy equals potential energy, and we find that relationship shown here.